Hey guys, welcome back to another week of New Horizon Tutoring ACT videos. Again, my name is Liz and we're going to be doing some math today. So I believe last time we finished up with powers, exponents. We talked a little bit about radicals and kind of tied it into log. So yeah, that's just kind of a recap of last time if you guys didn't remember. But now we're going to switch to a pretty entirely different subject. We're going to be talking about what are called conic sections today. You probably have, well, I hope you've seen at least like maybe 2 out of these 4 conic sections are what they're called. You just might not know that they're referred to as like conic sections in a general term. But that's what we're going to be working with today. We're going to be working out of the math packet that Manoj gave you guys specifically. So if you have that, go ahead, take it out. It's going to be page 11. And yeah, really what composes page 11 is just 4 different conic sections, and we're just going to go through each one. I'll write out the formula or the equation for each, kind of explain the differences between them, and then if we have any time at the end, which I think we will, we'll be able to get to some problems. And I'll mention when we like cover each conic section how often the ACT tests over each one, because it's not like the ACT tests the same amount over each type of conic section, just because some are a little bit more relevant, I guess, than others. But like I said, I'll mention that when we get to each conic section. So like I said, get your math packet out, the notebook that you've been working out of, graphing calculator, something to write with, and yeah, we're just gonna go ahead and jump into notes. Again, just working out of page 11 of that math packet. Okay, so the first conic section that we're going to deal with that you probably are like relatively familiar with, even if you haven't dealt with circles on the coordinate plane, you've obviously dealt with circles just in regular geometry. So that's called what they call plane geometry, I believe, just working on it, like area, circumference, all that jazz. A lot of times based around like word problems, stuff like that. This, on the other hand, like I said, is called coordinate geometry. And that's just basically because it's on the coordinate plane. Like we're dealing with the XY axis, stuff like that. So yeah, that's kind of what we're dealing with here, which is why that's basically what we have on here, right? Just a graph of a circle. So you technically can graph this in your graphing calculator. However, I'm not going to go through each individual step because it's not really helpful to the problems and we don't really need to know how to do it. But really all you have to know is that you can't type it into like your y is equal to mx plus b format, essentially, which is what you usually do for just like graphing normal lines, or y is equal to x squared, all that. You can't do that with this one, obviously, because it's not a straight line, it's a circle. So there's just some extra stuff with that. So we're not going to focus on the graphing aspect of it, but we are going to focus just on like the algebraic aspect and how changes to this equation, this like general base equation, are going to reflect in the graph itself. Okay, so just looking at that base equation, it reads as the quantity of x minus h squared plus the quantity of y minus k squared, I don't know why this isn't working, whatever, is equal to r squared. So I'm just going to kind of debrief and explain the many variables behind this equation. So x and y, just like any other time that you see x and y in an equation on a coordinate plane, just stands for any set of numbers that is on that line. It typically would be a line. In this case, it's really just any pair of coordinates that's on the circle. So that's x and y, pretty self-explanatory. H and K, on the other hand, are the coordinate pair. Together they make up the coordinate pair that is going to be the center of the circle. So that's obviously super important. And again, just paying attention to the fact that it's x minus h and y minus k. So I'll give you guys a quick example. Let's say we had like x minus 3 squared plus y minus 4 squared is equal to 1 or something. What a lot of people will do is if they give you an equation like this and they ask for the center of the circle, what a lot of people automatically do is say, oh, okay, this center is going to be -3, -4, right? Because that's what they see right here, -3 and -4. That's actually going to be incorrect, and that's, again, based on the fact that we already have a negative up in this equation. So technically, if the center was -3, -4, we would plug in -3 into this base equation and plug in -4 into the base equation, and our new equation would actually be x plus 3 squared and y plus 4 squared, because the double negative cancels out, becomes a positive. So whenever you see what looks like a negative number there, the actual value within the center is going to be positive. So just make sure that you keep that distinction clear. And that's just kind of an example to showcase that. And then, yeah, these two terms are being added together. Some of these equations of conic sections can get kind of repetitive, I guess, but they have like very slight changes. So just make sure that you don't gloss over the fact that that is being added together instead of being subtracted together, because obviously it wouldn't form a circle if it was subtracted. So yeah, that's the first part explained. Second part explained, pretty straightforward. It's just going to be the radius squared. And again, the definition of a radius is the distance between the center of the circle and any point on the outside of the circle. So I drew my radius like so. You can really draw it however you want, as long as it is a line that extends from the center of the circle to the outside of the circle. Okay, that is almost all I want to say for circles. One other thing that I do want to talk about is the concept of tangent lines. Okay, so I'll write this down. All right, so tangent lines, just very generally speaking, are essentially a straight line that touches a curved, I don't want to say line because technically curved lines aren't like straight lines, a curved equation at exactly one point. So there's no overlap between these two. I'll say this is my curved one. There's no like overlap between these two lines. It just like barely skims it on the top. So like, I guess I could do this right here. If I have my water bottle, obviously it's a curved, that's unfortunate. Obviously it's a curved cylinder, right? If we have our circle here, you can think of the tangent line as just like putting a pencil on it. So it just barely skims over it. That's just a brief explanation of what tangent lines are. And the reason that I'm bringing them up in this specific scenario is because they give us a lot of really good information with regards to our circle. So the reason that I drew this specific tangent line where I did is because it intersects with the same exact point that the radius does. And the fact that it does that allows us to do a pretty cool thing with it that's going to help us in solving problems. If we didn't know this information, we probably wouldn't be able to solve a problem like this. So basically, the rule is that if you ever have a tangent line in a circle or in relation to a circle, and that tangent line touches the circle at the same point that the radius does, the radius and the tangent line are going to be perpendicular to each other. So then we can kind of expand to ask, okay, well, what else do we know about perpendicular lines? We know that they have the opposite reciprocal slope, right? So let's just say that our radius, this little section right here, had a slope of m. That's typically the variable that we use when we're dealing with slope. If our radius has a slope of m, our tangent line is going to have a slope of -1m. So make sure that you just keep that in mind when you're dealing with circles, stuff like that. I actually believe that I have a problem that involves this. So if we do get to problems, either today or maybe next time or whenever we have a little bit of extra time, if we don't get enough time today, keep that in mind because it's going to be really helpful. And without knowing that, you won't be able to solve specific problems like this. Not all circle problems are going to include stuff like that, but I would say like a relatively good amount, and it's just really important to know. Okay, let's just go ahead and do this. All right, so that is, yeah, basically all I wanted to say on a circle. So now we're going to deal with ellipses. Oh, that's a very sad ellipse. That's Okay, so like I said, we're now dealing with what we call ellipses, which pretty similar to a circle, but it's just a little bit more oblong, so it's kind of like an oval. Ellipse is really just a fancy name for an oval. You guys might already know this, but fun fact, technically the planets travel around in elliptical orbits. They don't have circular orbits, so this is really important when you get into like actual real world application of this. Anyways, that's what an ellipse is going to look like, but it's going to be a lot more accurately drawn, but it's basically just an oval. There's a couple things that I want to point out about this graph. So we still have that same like formatting setup of our center. It's still going to be referred to as HK. Again, that's just the coordinate pair that stands in for our center. But we do have two other kind of components to an elliptical graph that we don't have when we're dealing with a circle. The first of which is going to be the length along the x-axis, and we're going to refer to that entire length as 2a. Or if you want to think about it, the length from the center to one of the edges along, again, the horizontal x-axis is just going to be 1a then. But that's typically how they like depict it in pictures. It just makes it a little bit easier to understand because it's just the entire length. But you can also, again, think about it in terms of just half of that. And then along the same line of thinking, but this time vertically on the y-axis, top to bottom of the ellipse is going to be referred to as 2b. So obviously when we like deal with actual examples of graphs with these, those numbers are going to be filled in. It's not going to be 2b and 2a. It might be like 14 and, I don't know, 6, something like that. So yeah, same thing applies. Technically, half of 2b would just be from the center to either the top or the bottom of the ellipse. Okay, so then relating that to our equation that we wrote below, it's pretty nice, right? I said that there was a lot of overlap between equations with conic sections, and hopefully you can see the similarities between the two. Because the top, at least this right here, is the same exact thing, which is super nice and convenient for our sake. We kind of just have to remember like bits and pieces and just keep the distinctions in their distinct categories because you can't mix them up or else you're going to get the problem wrong. So yeah, we still have the quantity of x minus h squared and the quantity of y minus k squared. This time they're just being divided by whatever that a value is squared, whatever that b value is squared. And I want to make a quick distinction, just to make sure that you have your actual a and your b value correct. So whatever value they give you for 2a is not going to be the number that you divide by here, right? Because 2a is not equal to a squared, like 99% of the time, unless a is equal to 2, but we're not going to worry about that case. Just know that whatever this number is here, you have to manipulate it a little bit to get it into this format. basically all you have to do, let's say, like I said, they gave you 2a, let's say it's 14. Divide 14 by 2 to get a, which is 7, and then square 7, 49. Pretty simple, you can do it in your head most of the time. Same exact thing goes for b. Again, just make sure you divide it, square it. And then another difference that you'll notice is that this is always going to be set equal to 1. No matter what our ellipse looks like, where it's positioned on like the xy axis, how big or small it is, it's always going to be equal to 1, which is kind of nice, right? Just standardizes it a little bit. And another thing that I want to point out that's going to make a little bit more sense in like 2 minutes, make sure that you remember that these two big terms here, these two big fractions, right, are being added together. And the way that I'd like to think about that is that it's, again, this is going to make a lot more sense in like 2 minutes, but it's coming together to form like one specific distinct shape, right? That one ellipse. So since they're coming together, they're being added, therefore these two separate terms are going to be added and not subtracted from each other, which is the other option that we have. Okay. I think that's basically all I want to talk about for ellipses. So now we're going to go ahead and move on to hyperbolas. Okay, sorry that took me a little bit longer than I anticipated to draw. I would like to think that I'm a good artist, but apparently not when it comes to mathematical representations. But anyways, just know that when you see hyperbolas, if you do see them on the ACT, they're not covered super heavily, which is kind of nice because they can be a little bit more confusing than the other three conic sections. Just know it'll look a lot prettier than that, so you don't have to worry about like interpreting it as much as you do here. But yeah, we're just gonna jump into talking about this then. As you can see, pretty stark differences between like the actual graphical representations, right? With our ovals and our circles, we had two different, between our circle and our oval, or ellipse, technically, we had different but pretty similar looking distinct shapes, right? Here, it just kind of looks like two weird inverted parabolas, and that's kind of what's happening, but when I explain it, hopefully it'll actually make a little bit more sense what's happening here, and why I drew these dotted lines in here, and what this weird box is doing in there. Okay, so basically what we have here is, well, I guess the first thing I kind of want to point out is the fact that even though it doesn't look like we necessarily have like a center to our shape, we still do. Even though our shape isn't one discrete shape, there's still going to be a related center in there. And again, that's just going to be referred to as HK. Nothing changes there. Even up here, we still have the format x minus h squared, y minus k squared, So that's gonna stay the same, which is kind of nice. But the next thing that I want to point out is what I referred to earlier, these two dotted lines. I don't know if you can see them super clearly, so draw them a little bit better. So basically what we have here are two asymptotes. And I'm trying to think, you guys may have dealt with asymptotes before if you've dealt with like radical functions at all, or sorry, rational functions, where you have like, let's say for example, x minus 2 over x minus 5, and you have to graph that. You're gonna have an asymptote. And basically what an asymptote is it's like essentially an imaginary line where your graph cannot cross. So that's what's happening here. It might look like, because of my drawing, that they cross in certain places with the actual green lines, the actual graph here, but as the graph extends in infinity, both directions, as it goes on forever, they're gonna get very, very close, right? But they're never actually going to intersect. That's just kind of the basic rule of asymptotes. So as we can see here, where those two asymptotes overlap is actually gonna be our center. So that's pretty helpful. It doesn't have like a specific purpose to know that, I guess, but like I said, it's just kind of good to remember. So yeah, we have our center there, and then, like I said, it would have been nicer if I could have drawn this more accurately, but I didn't want to pull out my ruler. So what we have here, based around the way that those asymptotes are aligned, is essentially the formation of a box, and it won't cross over with these lines. It might look like it does, but the main thing that you need to know is that this kind of like box, or this rectangle if you will, that is going to be what tells us our A and our B values. So again, A is still going to be x-axis, B is still going to be y-axis, and again it's 2A, 2B, side to side. You could technically divide it by 2, just as we did with the ellipse there. And another thing, like I said before, this is going to make a lot more sense now. The only difference between the equation for a hyperbola and the equation for an ellipse is what goes right here, right? Positive, we're adding these two terms together in an ellipse, and we're subtracting these two terms in a hyperbola. So like I was kind of mentioning before, that's why with ellipse it's easier for me to imagine them coming together, and for hyperbola, since we're subtracting them, it's easier for me to remember them like going apart, if that makes sense, because they don't come together. They go in two opposite directions along the x-axis and infinity both ways. So yeah, just keep that distinction clear. Other than that, it's never going to ask you, thankfully, to construct like a hyperbola or a graph for a hyperbola. Most of the time, it's just going to ask you, like, it might give you a graphical representation of it for any conic section, honestly, and then it might just ask you what the formula is for that. So I would say half of that probably is just remembering the actual formula, which is really nice for you guys, because it's pretty easy memorization. Like I said before, you can kind of do like some logical reasoning behind it and come to that equation, but definitely do make like a conscious effort to memorize them, because even if you're not like super strong in your ability to actually create the equations themselves, you could probably do process of elimination and knock out, I'd say, on average, like half of the answer choices just by knowing the correct equation and eliminating the wrong equations. Okay, I think that is all I want to say about hyperbolas and ellipses. So now we're going to move into some more familiar territory, thankfully. We're going to talk about parabolas. Okay, so like I said, this is probably a little bit more familiar, which is kind of nice. And also, just in general, I would say out of the 4 conic sections, it's a pretty close tie between circles and parabolas for which one the ACT is going to test over the most. I've seen a few problems with ellipses and maybe like 1 or 2 every so often for hyperbolas. So if you're a little confused on hyperbolas, I will admit they just are weird by their nature. Don't like get too upset or worried about it because it's going to be a very, very, very small fraction of what the ACT tests over. So your time is going to be better spent understanding more important topics like parabolas. Okay, so I have 2 different forms here for my parabola, but before I get into that, I'm going to briefly discuss the actual graph of it. Again, even though this isn't like the center of our parabola, we have our vertex here, and just like the other 3 forms, it's going to have the coordinate pair of HK, and I guess that really only refers to this equation, which we will talk about in a little bit. Other than that, you can tell that it has symmetry on both sides, right? And that is denoted by the axis of symmetry here, which I believe we already covered the axis of symmetry, but we'll kind of go over that equation in a little bit, just to refresh about it. Okay, so actually, one more thing that I want to talk about. Just remember that this A term, and this applies actually to both of these equations down here. That A term is going to deal with what we call concavity. And slope, and again I put slope in parentheses like I did last time, if you remember the last time that we like specifically dealt with parabolas. First thing, concavity, that's the actual sign of A. So if A is positive, your parabola is going to point upwards. If A is negative, parabola is going to point downwards. In this case, our A is hypothetically positive because it points upward. Even though we're not dealing with like an actual equation for this graph yet, we know that A would be positive in fact. And then slope, basically just how vertically compressed or vertically stretched it is, depending on like the actual numerical value of A itself. Okay, so that's a quick debrief of the graph. Now getting into these 2 different equations. Okay, so there's really 2 different names to which we can refer to these different equations. The first of which that you're probably more familiar with is going to be standard. Standard you typically deal with like when you're trying to find the roots of a parabola and you're not really dealing with the graph. It's more algebraic, right? Because we can factor that pretty easily, hopefully at least. Super useful skill to have. So yeah, that's typically when we use standard form. But a lot of times you will see this form, right? The other form that I wrote down here, it's called vertex form, which makes sense because it explicitly has that vertex in there. And it doesn't have the values of B and C. So, like I said, a lot of times you'll deal with vertex form when you're graphing. And again, it kind of just depends on what the answer choices dictate. So whatever form the answer choice is in, that's what you're going to roll with. Let's say that would be in like a question that was asking you to find the actual equation for a parabola. One thing to notice is that we do have x minus h squared here, again following that same pattern that we did for the other conic sections, but we have plus k here. So just make sure that, again, as with everything, you keep your signs distinct and in order. Okay, I think that is basically all I want to go over for notes, which is awesome, because now we have roughly 9 minutes to go over some questions. So I'm going to erase this, write a question up on the board, brief explanation, and then we'll go through the answer. Okay, so this one's pretty straightforward, and I know that you technically wouldn't have to like draw a sketch of anything on the ACT, but what I've seen them do quite often actually is give you a problem just like this and say, choose the sketch of this equation, and then it just gives you 5 different sketches. So it's basically the same thing, it just saves me the hassle of having to draw out 5 different sketches, and you guys can practice your graphing skills, basically. Okay, so not too long of a problem, so we're gonna go over it super quick. First things first, we know we're dealing with conic sections, right? And this one is pretty obvious to see that it's gonna be a parabola, just because we've worked with parabolas a little bit more. And if you notice, this is gonna be in standard form, right? Which is pretty nice, especially because it doesn't have an x term here. It just has x squared plus 5, or technically -1/2 x squared plus 5, but that's gonna help us out a lot in how easy it is to graph it, and I'll show you that in a second. Okay, so first things first, just draw my xy coordinate plane, and the first thing that I'm gonna look at is, well, if this was like a more, I don't wanna say normal, but like a more representative problem about parabolas, basically just saying like, kind of your average draw the parabola problem, it typically would follow the format of something like x squared plus x plus a coefficient number, or just like a tack-on number at the end, but it doesn't here. So that would be the first thing that I would look for to see if I could factor that out. Since we don't have an x term here, we actually can't really do our typical factoring, right? Which is normally what we would do, set 2 parentheses, x minus a number, x plus a number, whatever the specific equation dictates, set it equal to 0, find the zeros, and then graph that. Or if we had our graphing calculator, we could honestly just type this in. But I do want to show you guys this super quick, just to reiterate some of these concepts that we're dealing with. So like I said before, since we don't have to actually factor that out and find the zeros, which is again just where the parabola crosses the x-axis, I'm really just going to start with my y-intercept. So that's one other really nice thing about standard form, is that it gives its y-intercept to you, which is super nice. So we have that plus 5 here, so I'm going to say this is roughly where 5 is on my y-axis. Next thing I'm going to do is look at my coefficient of my x squared term, because again, 2 different things that's going to tell you is the concavity, whether it's concave up or concave down, and whether it's vertically compressed or vertically stretched. So first thing, I know it's going to be concave down because it is a negative number, and I know that it's going to be vertically compressed because it's a fraction smaller than 1. Okay, so that's kind of like a rough estimate of what that would look like. If you drew something like this, it's good stuff, we love to see it. But yeah, that's just kind of the thought process behind that. Like I said, if I was given this exact problem in the ACT, I might just throw it on my calculator to be safe if I personally know that like I can graph it super quickly. Other than that, I really don't think it would be too difficult to use process of elimination, look at the answer choices, figure that it's this from this equation, because it's really all given to you. We didn't have to do necessarily any like manipulation with this. Okay, I think we have time for maybe one more brief problem. Okay, so this problem basically just wants us to write the equation of a circle with a center at 2, -3 and a diameter of 10. So since we're getting pretty close to time, I'm just going to brush through this pretty quickly and explain it. So first things first, I'm going to write out the general equation of a circle, which again is just x minus h squared plus y minus k squared is equal to r squared, where h and k are going to be my center. So that's really what I'm going to deal with first. Tells me that the h term for my center is just 2. So I have x minus 2 squared here plus y, and as you can see, that term is going to be -3, right? So we would technically have y minus a -3 squared, but since we have a double negative here, that's going to turn to a positive. So that's just one example of how you have to really watch your signs when you're dealing with stuff like this. And then the last part, we have to incorporate our radius, but it doesn't tell us our radius, it tells us our diameter, which is really not all that difficult. We just know that to go from our diameter to our radius, we have to divide by 2, right? So we divide by 2, we get 5, and then since it's r squared here and not just the radius, we actually have to square that, which is going to get us 25. So then this is going to go ahead and be our final answer. Which I would say that this problem in general is pretty representative of what a lot of problems with conic sections are going to look like. They'll either just kind of like give you the information, or they might represent it graphically and say, okay, from this graph, write me an equation. Again, one of the main themes behind it is actually being able to write those equations. So, like I said, there's 2 main parts in that. The first of which is memorizing the equations, and the second of which is understanding the equations and knowing how to manipulate them based on the information that they give you, either flat out or in a graph. Okay, so we are almost at 40 minutes, so we're going to go ahead and call it a day. Again, I would just say my closing words for this. Spend a little bit of time with this, look over the graphs, look over the equations, try to memorize them if you can, and again, just think logically about it so it's not pure memorization, but you can kind of reason your way through it in the actual test. Okay, awesome job today, guys. That's going to be it for this week, and we will see you guys next week.